mathematical complexity. So this is showing you that pure mathematics is even more biological than biology is, and this is a very concrete example of that. So yeah, I mean, I think physicists tend to be sympathetic when I talk about these ideas, because you know this business of God plays dice and quantum mechanics is very familiar, even in classical physics with chaotic dynamics, right? We know that randomness is everywhere in classical physics and quantum physics, and we know that we can work with it, we can live with it, we can use it to our advantage. Even when we can apply statistical arguments, we can understand systems that we couldn't understand if we really had to calculate exactly what they do, but we can understand statistically, we can make statistical predictions. But this kind of viewpoint in the world of pure mathematics really looks pretty bizarre to pure mathematicians, and especially to logicians. This is very interdisciplinary work. Okay, so I've used up most of my time. The next step is taking these ideas, and so this is a completely different view to what is called metamathematics, which is sort of mathematical self-criticism. It's mathematics looking at the power, trying to evaluate the power of mathematical methods, and in particular of formal mathematical theories, axiomatic theories. Okay, and I'm using ideas which are ideas from in a way, they're thermodynamical-like ideas, or they're versions of entropy notions. So it's sort of looking at a mathematical theory like a heat engine. This is sort of kind of the flavor of this. Okay, so the third topic I promised to talk about is biology, and in fact, this stuff that I'm telling you is really very old. You know, this result that you can't prove the program is elegance, I published a version of that in Scientific American in 1975. And the halting probability also goes back decades. I fortunately have something new to talk about, and I'm very pleased to have an opportunity to tell you about it. That's the question of applying some of these ideas to biology. You know, biology is the field of science which is being developed most at this point. It's really a very, very exciting moment in biology. And as a pure mathematician, I find it unacceptable that there is no deep mathematical theory of biology, of evolution. And you know, the honor of pure mathematics requires us to be able to do such a thing. Another way to put it is, if you look at physics, mathematics is very, very relevant to physics, right? Theoretical physics is beautiful, it's really deep, important mathematics. But in the case of biology, you know, what's going on there? So the idea would be to have a kind of a theoretical biology that is like theoretical physics. That's the proposal. But, you know, I don't think this is possible because biology is just a mess. It's a million-pound marshmallow. It's not very mathematical. Anything goes, you know, you'll find, no matter how weird an organism, someplace there's an ecological niche where you find an organism like this. There are always exceptions to any rule. So I'm proposing a toy version of biology again. You saw a toy version of what physics is and a toy version of what mathematics is. I'm proposing a toy version of biology. And this toy version is basically looking at DNA like a computer program, so that's not very new. You've all heard about it. But, right. Let's go to biology now and make a software model of what goes on in biology. So this is a new field. I've only been working on this, Virginia and I have only been working on this for 3 years, and it only started working about a year ago. And almost immediately, Professor Martin-Delgado got involved. So he's the first person outside of our little group to do work in this area, to have a paper in this area, which is why we're thrilled to be here. So what is the idea here? Well, let's look at population genetics. How about a theoretical biology? Well, there is population genetics, and it's beautiful mathematics. It's the wrong kind of mathematics, in my opinion. It's continuous mathematics. Remember that I threw away continuous mathematics earlier in this talk? Well, another way to put it is, what about the problem of biological creativity? I think it's a really central issue in biology that has somehow gotten lost, biological creativity. if you look at population genetics, which is a well-developed, beautiful field, the definition, you'll find one-sentence definitions of population genetics, and the definitions go like this. It's the study of changes in frequency of genes in a population in response to selective pressure or competition. And by definition, you have a fixed, finite pool of genes. And all you're looking at is the change in the frequency. Well, that's important, that's great. You write down differential equations and you get lots of beautiful stuff. But where do new genes come from? It doesn't. You can't discuss that in this theory. You see. So the question is, what kind of mathematics can we use to look at biological creativity, or in a way say, where do new genes come from? And I think what we need is algorithmic mathematics, and the reason is that DNA is sort of a computer program. And I think one very central issue in theoretical biology should be to understand evolution, right? I mean, we all agree that evolution takes place. The question is Darwin's theory enough to account for that or not? The experimental evidence in favor of evolution taking place is enormously great and was appreciated before Darwin. So you can use this idea to make a computer program. So I'm proposing that to model biology, to make a theoretical biology, the first step is you need to have some mathematical object that you can use to model the space of all possible organisms. And I'm proposing you take the space of all possible computer programs in a programming language. Technically, it would be a universal programming language. Most programming languages are universal in the sense that any algorithm can be written in them. And DNA seems to be that powerful. So the idea is you take as your space all possible algorithms, all possible programs. It's going to be a software space, in other words. So I'm proposing we develop a theoretical biology using a software space. And so basically, what are my organisms? Well, they're just DNA. I'm forgetting about metabolism. This is a toy model, right? I'm going to forget about metabolism and energy and just look at information. So my organisms basically have no bodies, they just have DNA. So they're just software organisms. And I'm going to do random mutations on the DNA and have a fitness criteria and see if evolution will happen or not. That's sort of the idea, to see if, how well. So in other words, real evolution is about, at least Darwin says, or the modern version of Darwin's theory says, real evolution is about making random changes in DNA and having natural selection apply to those random changes in DNA. Now, DNA is a very complicated programming language that we don't entirely know, so to make a simpler theory, I'm going, instead of making random changes in natural software, because DNA is a digital software, digital programming language, essentially. I'm going to be making random changes in artificial software, in a computer programming language. And then you have to have a fitness criterion, and which gives you selection of the survival of the fittest. And the question is, to study mathematically if evolution will take place or not. And now to make this model, so I only have software organisms, and one of the things I do in this model is I sort of forget about the environment and I forget about populations. I just have a single organism. Modeling, interaction between organisms or interaction between organisms and the environment is complicated. So to start off, I want to have the simplest system I possibly can. So there's basically just a single organism, which is a software organism, and it has a goal in life, which is a mathematical problem. And I think I've used up, have I used up most of my time?
Yeah, but you may finish an introduction for the next lecture.
The rest of the week we're going to be talking about these ideas. So just to introduce these ideas, the idea is to think of DNA as a computer program, and instead, the way that Darwin in his first chapter of his book talks about the fact that artificial selection works. He was a wealthy Englishman living in the country. His neighbors had racehorses, and they had beautiful roses, and they had cows that produced lots of milk, and everyone there knew that by selecting the cow that produced most milk, or the most beautiful rose, the fastest horse, the breeders could get animals that were better for human purposes. So he said, maybe that's what happens in nature. Maybe in nature there is natural selection, not artificial selection done by animal breeders or plant breeders, and due to Malthusian limitations, right? So this is his analogy, which is the basis for his whole theory. So the basis for this theory is also an analogy. Instead of looking at the result of a selection applied to random mutations on